Hi everyone, it is my pleasure to be here to present my work in the 59th SciENce Annual Conference. My name is Jati Wowo Jamari and my co-author is Muhammad Raushan Fikri. We are from Sampoerna University in Jakarta, Indonesia. Our work is titled Scalable Formation Control of Double Integrator Agents, a Distributed Observer Approach. These are the outline of our presentation. I will begin with the introduction. Multi-agent formation is an active area in cooperative control of multi-agent systems, as we can see and in these works. Scalability is an important feature in multi-agent formation, as we can see in this example. So this example shows three agents forming a triangle formation that tries to move a narrow passage. They resize their formation size so that they can move through the narrow passage. So this resizing is also called as the scalability. And the scalability allows for adaptability of the group to the change in mission and environmental condition. Past works on distributed scalable formation consider undirected network and also directed network with k-rooted graph. This work considers double integrator agents under directed network where directed spanning tree is necessary and sufficient conditions. Now I'll explain about the graph notations and also problem formulation. The graph is used to model the interaction network among agents, and we are using the standard definition and notation on graph in this work. L here is the Laplacian matrix, where Lij is minus Aij for I not equal to j, and Li to be the sum of Aij. Aij here is the agency matrix entry. Graph G contains a spanning tree if there exists a directed path from at least one node to every other node. So this is also a standard definition on spanning tree on graph. For the problem formulation, we consider n double integrators given by equation 1. Xi here is the position, Vi is the velocity, and Ui is the control input of agent I. Extension to higher dimension problem is possible by using Kronecker product operator. The objective is given in here. Let xid for all I to be desired position of agent I on the local coordinate system. The objective is to design Ui in equation 1 such that for any initial states, the equation 2 holds. Ct0 in equation 2 is the scaling factor of the formation that depends on initial starting time t0. Equation 2 also means that asymptotically, relative position between any two agents are equal to the relative desired position multiplied by a scaling factor Ct0. Now we'll begin with the main result. The proposed control input for this work is given by equation 3. So in equation 3, we have k here is a design variable. V is the velocity, as we also explained earlier. And x hat here is the estimate of xi that we obtain from distributed observer given by equation 4. And so from equation 3 and 4, only relative position of agents is needed in the control input. If we let x, v, and x hat to be the stack factor, and we also let e as the error between the position and also the estimate of the position, the overall system of n agents can be expressed as equation 5. L here is the Laplacian matrix, phi is the Self Loop Laplacian associated with graph G and also formation factor xd, with Vii equal to Si, Vij equal to minus Aij for I not equal to j, and R here is a diagonal matrix. And the entry of R and also Si is given in this equation. So in equation 6 and 7, we can see that the desired formation of agents are embedded in these two variables. Before we give our main theorem, we need two theorems on the spectral properties of the matrix of importance. The first theorem is the spectral properties on Self Loop Laplacian. And from this theorem, we can see that actually the spectral properties of the Self Loop Laplacian is the same with the Laplacian matrix, except that the right eigenvector of the matrix phi is xd as compared to the vector of all one for the Laplacian matrix. That is correspond to the zero eigenvalue of the Self Loop Laplacian, but the rest are the same with the Laplacian matrix. Also, this theorem for the spectral properties of this matrix is also needed. I will explain later why this spectral properties is needed. So, if we let this theta to be this matrix 0 identity minus phi and minus k identity, and also mu I is the eigenvalues of minus phi. So minus phi is the minus of the Self Loop Laplacian, and Re and M here is the real part and imaginary part of some variable. If we let also xid to be positive for all I, then the matrix theta has these following properties. So theta has m0 eigenvalues if and only if minus phi has also m0 eigenvalues. Also, if we let k to be chosen such that this equation 8 holds, then the non-zero eigenvalues of the theta has negative real part. And this is the main theorem of our work. Consider the n systems of double integrator given by equation 1, where the control input ui is given by equation 3, with k given by 8, equation 8 that just now discussed, and the distributed observer given by equation 4. Let xid to be positive for all I. The scalar formation is solved if and only if graph G contains a spanning tree. So to prove this theorem, we simply analyze the overall system that is being discussed earlier. So to analyze this system by using the linear system standard analysis, we need the spectral properties of this matrix. So this matrix is actually the matrix theta that is discussed in the earlier theorem. So by having the spectral properties of theta here and also the Laplacian matrix, we can analyze the asymptotic value of x, v, and the e. Yeah. Also, to do the analysis, we also need the left eigenvector of these two matrix theta and L, that we mean correspond to their zero eigenvalue. The formation scaling factor will be discussed in this slide. So suppose the main theorem holds, then the steady state position of agents can be shown to be in this expression. In here, C2 T0 is the common bias term that applies for all agents, while C1 T0 is the formation scaling factor, and it is found to be in this given in this expression. In here, y phi transpose is actually the left eigenvector of the matrix phi corresponds to the zero eigenvalue of matrix phi, which is why this relation holds. Yeah. Okay. And so we can see here that the formation scaling factor, which is C1 T0 or CT0, depends on the graph topology, which is represented by y phi transpose here, and also depends on the initial position, initial velocity, and also initial state of the estimator, because we have the error term here between x and x hat. Yeah. Without loss of generality, suppose graph G is a leader-follower graph with node n as the leader node, then y phi transpose can be expressed as this expression in here. If we suppose also k equal to 1, then the formation scaling factor can simply be expressed as this. So only agent n can affect the formation scaling factor, and this is directly related to leader-follower graph with node n as the leader node. Now we will discuss about the numerical examples. For leaderless graph example, we have formation, desired formation on x-axis and y-axis. So this problem is on a 2D problem in x and y-axis. And this is the graph configuration for the numerical example. And for two different initial position, we get a different formation scaling factor. So based on this desired formation, rectangle formation is formed, but the x and y-axis scaling factor are different. So the formation form is a rectangle. For the leader-follower graph example, we used similar x dx and x dy, which are the desired formation factor. But then in the middle of the simulation, the formation scaling factor is changed. Yeah, so this is the graph configuration, and this is the result of the simulation. So initially, the formation scaling factor is 1, which is given by this yellow square. And then after some time, when the formation is reached, agent number 4 changes its initial states on the estimator, so that the formation scaling factor is 0.25. So in the end, we reach this green formation. So changing the scaling factor of the formation is possible when the graph is a leader-follower graph. Yeah, so that is possible by having only one agent to change the scaling factor of formation when the graph is a leader-follower. For the conclusion and future works, a new method of distributed formation scaling factor for double integrated agents on the data network is presented. Spanning tree condition is shown to be necessary and sufficient condition for scalable formation. Possible future research direction include moving in scalable formation as illustrated in this figure, and also extension of the proposed method to linear agent model, and also to consider measurement error, because we need to measure the velocity of agents, and measurement error may also happen in the operation. So in the future, we'll also consider that in the work. Thank you very much for all of your attention.